My name's Chris Woods. Densification Inc.'s based out of Virginia, but we are pretty much at this point a nationwide contractor. I mean, at one point last summer, we had cranes running between Anchorage, Alaska, and Puerto Rico. So we kind of move our cranes around the site, around the country as needed. So what I'm hoping to do today is just kind of give an overview of the dynamic compaction process, how, where it's applicable, the basics of design, and just kind of run through a couple examples of sites where we had variable different kinds of soil conditions, really just to kind of make it so that it's another tool in your toolbox, something you're aware of as a technique that may ultimately be usable on your site. So with that, we'll get into it. There we go. So I'm going to go through just again talking about the various types of soils that you can target for dynamic compaction. So we're going to go through, what kind of soils you can look for to implement this technology. Go through the principles, basics of design. As you can imagine, dropping a weight from the sky, there's not a ton of in-depth calculation here, but there is definitely some design principles that go with it. As you can also imagine, dropping a big weight on the ground, there could be some construction phase issues that you would need to deal with. So kind of talk through some of them. And then, like I said, just go through some examples of some sites and what the different soil conditions were there that we had to contend with. All right. So when you're thinking ground improvement in general, basically it's loose, soft, low shear strength type of materials, urban fills, peat, clays, sands, those sorts of materials. So what can you do, right? Building code generally doesn't allow the just do nothing and hope it doesn't settle option, right? You can take all these unsuitable soils out, replace them with structural fill. If you've got material that can be reused readily, maybe that's okay. But if it's landfill or contaminated or something like that, disposing of that kind of material can be pretty costly. You can go the deep foundations route and just bypass that layer altogether. Or you can get into ground improvement, right? And modify the soils to make them suitable to support whatever structure you're building. Okay. So when we think of ground improvement, the way I like to kind of think about it, you got really two avenues you can go down. A densification based approach, which is you're taking a soil mass of a certain area, a certain depth, and you're physically improving the engineering properties of that soil, or you're making them more uniform. The alternative is going down like a reinforcement-based technique, which would be more of your aggregate piers, your rigid inclusions, jet grouting, compared to the densification-based approaches. Okay, so when we talk specifically about dynamic compaction, the kind of the most common soils you're talking about, loose sands, uncontrolled fills. But we do get into specific applications, debris fills. There's a lot of work on landfills these days, liquefiable soils. In the eastern part of the country where you get into the karst regions, you can, get into going after some of those sinkhole type features, preparation of landfill. So you can see from this slide, I mean, there's a lot more than just, all right, we got some loose sand that we need to densify. All right, so a couple terms that I'll probably reference as we're going through just to keep in mind. When we're talking effective depth, we're talking what's our depth of improvement that we're targeting, right? There's two ways of looking at energy. The energy level would be you got to weight and you got to drop height, and that's your energy per drop, generally in ton feet. Right? Total applied energy, which we'll get into with the FHWA sort of design approach, is if you think of it this way, you've got a sort of rectangular cube of soil, right? You've got an area of a building and a depth you're trying to improve. Your total applied energy is essentially your energy per unit volume that you've got there to make that soil, useful. And then pounder, tamper, I mean, basically that's the weight that you're dropping, and we call that all kinds of different things, right? This is generally when we're asked to show up to the site, this is what we bring. We bring our crane, we have our operators, the pounder. It's a pretty small operation. Generally, one crane, two operators, and a superintendent is our crew. Okay, so this here is an excerpt from the FHWA manual on dynamic compaction, and essentially what you can see here is kind of broken up into 3 zones based on grain size. Zone 1 is everything that's generally to the left of the -200. Zone 2 is kind of, you're getting into that gray area of you have to have the right characteristics for it to work. And then zone 3 is very plastic soils, which is not really going to be conducive to improvement through a high energy application. All right. So when we're talking dynamic compaction, what are the advantages to this, right? The main thing of any ground improvement really is you're trying to get to a point where you can use shallow foundations in lieu of the more costly deep foundation options, right? As it relates to areas of liquefaction concern, right? We have done jobs where they're going to be deep foundation jobs, but because you have this fill layer at the surface, you're getting low lateral capacities on your deep foundation elements. So we may still pound a site just to tighten up that upper, 10 pile diameter zone where you're going to drive your lateral capacity of your deep foundation elements, right? When we're focusing just on the shallow foundation options, again, you're looking to reduce settlement, make it manageable, increase your bearing capacity. Something else to think about also is, as I pointed to before, if you've got an impacted soil from an environmental standpoint, that may be real costly to get rid of. And so coming up with a solution that allows you to improve that material in site, in place, and not have to remove it can be, the difference between a pro forma bust on a job or it going forward, right? And then one of the last things is, as you'll see some of the pictures with the grid spacing and the craters and everything that's formed by this, you're basically watching real-time, you're getting real-time data of the program. And so, you're able to sort of address areas that don't look the same as everything else kind of right as you're there. So it's considered like a self-compensating type approach, right? So a typical program could be a weight anywhere from, generally 5 to say 25 tons, 50 to 100 feet. If you start pushing higher than that, that generally gets outside the range of what's considered readily commercially available, at least, right? Mostly applicable to granular sandy deposits, but as I pointed out, there are some specific clay, karst, type applications that you can use. Generally 25 feet or so is where I feel pretty comfortable getting an improvement. You can push the upper end of that 25-ton weight, maybe get up to 30 feet if the soil conditions are right. But if you're looking for something deeper than this, maybe you need to be thinking about a vibro option or rigid inclusions or something that can get you a deeper level of improvement. Shallow groundwaters is something I get asked about a lot because, again, you're introducing a lot of energy to the ground. So if that energy is there and you've got shallow groundwater, you can build up excess pore pressures that may require multiple passes over time to allow for that excess pore pressure to dissipate. And then, as I pointed out before, dropping a big weight on the ground, you're going to generate vibration levels. So that's a pretty significant concern. Right. So here we just kind of have a few schematics of the process. You can see it's kind of like a conical distribution of the energy under the weight. Right. Here's another illustration. And what you can take away from this is you see the yellow and the green circles at the surface. Those would be the crater locations. And what you can see here is kind of the idea is that these cones of influence under the crater zones, you design it such that they all basically overlap, and that's how you're making sure you're improving your entire mass, right? So 2 formulas, 2 design criteria to kind of keep in mind. Your depth of improvement is going to basically be your weight times your height times an empirical factor. And you can see there the range of that's 0.35 to 0.6. And the easiest way to think of that is 0.6, the higher end of that empirical value is really like a clean sand that could transfer energy pretty easily. 0.35 is like municipal solid waste, where there's a lot of voids and you're probably collapsing voids more than you're transferring energy particle to particle. So you could see that for the same weight and height, your depth of influence for a landfill project is going to be significantly less than it would be for a sand, right? So this is the, one consideration. And then this gets into your applied energy, where you're just considering your number of drops at a point, your weight, your drop height, how many passes you're doing, your grid spacing. And this is how you get at that kind of, energy per unit volume that I was mentioning. Right. So when we talk, again, referring back to the FHWA manual that was written by Bob Lucas, those 3 zones that we saw on the grain size distribution thing, 2 to 250 is kind of the lower end kilojoules per cubic meter, all the way up to the landfill material, 600 to 1,000. So you could see, again, for the same level of improvement, the amount of energy that needs to go into a sandy material versus a landfill material is significantly more. And these are, again, just some target ranges of energy that when you're designing a program, you would want to see. Right. So what are some other design considerations? Well, it always, and this, whether you're doing deep foundations, whatever you're doing, you want to know what was on a site before. Particular to the vibration concerns here, boundary conditions, what kind of buildings, utilities, things like that are of concern. Your subsurface conditions, understanding what kind of settlement criteria is in place from the structural engineer, and then, schedule plays into things as well. So, from a historic site usage, understanding if there's old foundations, old structural elements, environmental concerns, right? If there's a lot of foundations in play and concrete in the ground, dropping a weight on that is more of a demolition activity than a ground improvement activity. And so that could be a real problem, from an, carrying the program out sort of approach. And then again, the environmental concerns, knowing how to handle the soils, do they need to stay on site? All things that play into designing your program. Boundary conditions, right? So I get, as a specialty contractor, I get a lot of phone calls from geotechnical engineers saying, hey, can you take a look at this site? What do you think? And what I always say is I need a geotech report or borings, and I need an address to look it up in Google Earth, right? And Google Earth is going to tell me, do I have nothing for a mile? Am I in the middle of a neighborhood where there's 50 houses within 75 feet that, basically everyone's going to get sued because you're going to be rattling china off the walls? Or are we in an industrial zone where you got another warehouse a couple hundred feet away and it's something you can manage, right? So that is a very important thing. I may have the perfect soil conditions on a site to implement dynamic compaction, but if it's for a school that's going in the middle of a neighborhood, sorry, call the aggregate pier guys, because that's, it's not a good scene for everyone at that point, right? Again, I touched on plastic soils not really being suitable. Shallow groundwater, really, it plays more into schedule, allowing dissipation in between passes, things of that nature. You may come into areas where you have soft zones that maybe we get into more of what we consider like a dynamic replacement, where if all of a sudden you're working away across a site and the craters are all 4 feet deep and you get to an area where they're 8 feet, that's not a uniform condition. So maybe we need to throw some, recycled concrete or something in those craters, pound them again to kind of get to that sort of, stable, uniform condition that we're looking for. So here's a picture. I really like this picture. This is a job we did down in Florida. And basically you can see sand boils coming up. And this was a very sandy site with shallow groundwater. But what this tells you is that you're liquefying those soils and that the process is working. You're building up this pore pressure, you're liquefying it, you're densifying these soils. And this is, that pore pressure, excess pore pressure alleviating itself, right? All right, so from a settlement standpoint, granular soils, we know that the majority of the post-construction settlement happens as the building's going up, compared to, more compressible soils that are going to settle over the longer term. The thing to remember, and I know I'm probably preaching to the choir if I'm talking mostly with geotechs right now, is ground improvement doesn't eliminate settlement. And so if you've got a site that is one of these warehouses that's got super flat floor requirements and electronic racking systems and all this other stuff where they can't really tolerate differential settlement. That plays into, can you use ground improvement, or am I looking at a structural floor slab? So it really is important to be having those conversations with the structural folks to make sure that everyone's on the same page going into a program like this. From a schedule standpoint, dynamic compaction, per crane, you can be doing 5 to 10,000 square feet a day. Winter weather is a bit of a deal breaker, right? You can't really be dropping a weight on frozen ground, because then you're really doing nothing but trying to bust up frost, and you're not really doing any ground improvement. So the northern half of the country, we're in that time of year where a lot of jobs actually get shut down if they're in the middle of the job, or you just kind of wait till March till things start thawing out a little bit. So construction phase. There's the real-time quality control that goes on, looking at crater depths, looking at surface elevations. Is the ground lowering, indicating that you're densifying it? When you're doing 5 drops at a point, is the decrease in the penetration with each drop getting less, indicating that you're getting that sort of gradual improvement? Are you seeing pore pressures build up? These are the kind of things that between the on-site inspector, my superintendent, always kind of looking at, just to verify that the work we're doing is passing that initial smell test. And here's, one job I did in Jersey, and I know it's, there's some small writing on it, don't pay attention to that, but what this communicates, or is meant to communicate, is that you see the different colors. Those represent different ranges of depths. And so this was very helpful when we did some post-improvement testing. And based on those results, we were able to go back in and correlate the results we weren't as happy with, where, with the deeper crater zones and things like that, where, it was showing that it was, a looser material. Okay. Lots of different types of testing can be used. It's really kind of dependent on the type of material you have. CPTs, SPTs are pretty common. We're doing a lot of work on landfills right now where, 50/2 from an SPT before and after doesn't really tell you anything. So you get into more some of the larger scale embankment load testing or things like that to get data, so you're comfortable with what you got. Vibration levels. This is a scaled energy factor plot, which is kind of like the first, pass at what are my vibration levels going to be. And those lines you can see are all, they're empirical data that's been generated on other sites. And if you come in on the bottom, knowing what your energy, your distance away to a structure is, you can come up to one of those lines depending on what kind of soil it is and get a sense as to what your particle velocities are going to be during this work. And so this is kind of a good first test of, do we have an issue or not? Once you get past that sort of desktop study, you collect what's called a site-specific attenuation curve. We do this at the beginning of most jobs where we do drops at 25 feet, 50 feet, 100 feet, collect that data on site so that we know as we move our way around the site, if we're getting closer to something that's a concern, what measures might need to be taken. Okay. It's just a bigger weight. Here you see a couple of examples. This was an instance where we tried out sheet piling as a vibration mitigation tool. This is probably the most common seismic isolation trench, where if you're dropping on one side and you're trying to isolate the vibrations to something, a utility or a structure on the other side, this helps mitigate your vibration levels considerably. And when we take a look at this chart here, you take a look at the red lines and the blue. So the red lines are kind of in front of the trench, behind the trench. The blue lines were in front and behind the sheets. And what it tells you is if you're at 100 feet, you've dropped your vibration level from 2 inches a second to less than a ½ inch a second. So again, this was just one specific site, but it's really kind of meant to illustrate the effectiveness. Okay. So to just kind of run through some quick pictures, see what the different soil conditions would be. Here's a job we did last year down in Puerto Rico where we were, it was all sand. Very much the concern was just liquefaction. This is a job we actually did up a couple years ago in Maple Grove, Minnesota, where it was on a former precasting plant, and you had all these different precast panels and stuff in the ground. And so the concern was voids around some of these panels. And so we used a pretty big weight to try and, make sure any of those voids were collapsed. Dredge fills pumped in a loose state need to be compacted. Here's an example in Pennsylvania where I was talking with karst, right? Karst is basically limestone topography where sinkholes can open up. And so the Cadillac solution is always going to be drilled piles, some sort of structural floor slab, eliminate, sinkhole concerns. Sometimes the middle of the road solution might be going after solution zones and pounding a bunch of stone in the ground until it kind of tightens up. So this is we don't do this a lot, but it's definitely an application that's out there. Here's a job we actually just finished up on Monday down in Arizona. You could see how close we are right to a highway, and you can see on the weight there, we've got a blast mat, a steel blast mat draped over the weight to really, help prevent material from getting thrown onto the street. But, we were able to work right next to a roadway. This is another job, highway job in Arkansas. Again, that's a little bit better picture of that blast mat that we use to help mitigate material being thrown on impact. Another sandy site in New York. You can see what the good crater formation looks like. We do a lot of work in Jersey. Again, a lot of uncontrolled fills in reclaimed areas, especially near waterfronts over time. Job at an airport out in Queens, out at JFK. This was all liquefiable soils. Long Island has a lot of liquefiable sands out that way. Here's a nice aerial. This is a job down in New Mexico. Another, you can see how close we are to the highway here. Roadway embankment going in. We do a lot of stuff down in Florida, a lot of loose sands, a lot of filled in lakes, things of that nature that are all pretty much in an uncontrolled scenario. Chicago, the old coal tunnels beneath the city collapsing under the highway, under Lakeshore Drive. This is a job I was involved with in China, a little bit different setup, but just a neat picture nonetheless. This is how deep some of the craters get sometimes. This is out San Francisco area. Turkmenistan, this was a major natural gas plant out in Turkmenistan in Southern Asia. Again, some dredge material placed in behind a cofferdam and compacted. And then this was a job where the field inspector was really kind of giving us a hard time about the way things looked. And so we handled it. So with that, I think I'm pretty much right at about 1 o'clock.
All right.